Thanks for the invitation. This is joint work with several people. So at the moment, it's mostly joint work with Andrew Duncan, who is a postdoc at Imperial, and also with Tony and Francis Nier. And then it's based also on earlier work with Michaela Tober. There is already a typo, so it's at here at Watt, in fact, not at Imperial at the moment, and Karel Pravda-Starov. Right, so there is some ongoing work that hasn't been submitted yet, but sort of the what I will present is based on earlier work with Tony and Francis that appeared in the Journal of Statistical Physics, some related work with Michaela Tober and Karel Pravda-Starov, and some ancient work that, well, basically I actually won't talk about it now. So I don't think, oh yeah, okay, here it is. Yeah, and this work is funded by this by the APSRC through these grants. Right, so for my sins, I decided to write a book, and well, it appeared, and if you want a PDF file, just let me know and I can send it to you. So, yeah, I'm recorded. Yeah, now that I think about it, yeah. Okay, I didn't say this, yeah, sorry. So don't email me and I won't send you a PDF file. So, yeah, so I always hope I can move to sort of one of the expensive neighborhoods in London, and yeah, if you buy this book, yeah. Right. Okay. So yeah. So yeah, this is not to become a millionaire by writing a book on mathematics. Right. So if you yeah. So what I want to talk about is about some techniques for sampling from a given distribution. So given up to a normalization, the normalization constant, and I want to discuss about sort of possible techniques for either accelerating convergence to equilibrium when we start from a non-stationary state, and then also reducing variance. Okay? Of course, all these problems have been studied a lot, and there's an enormous literature in this subject. So the main idea that I want to focus on is that if we choose the right Markov chain, if you like, to use in order to perform our Markov Chain Monte Carlo estimate of the distribution, then by choosing it the right way, we can correct the bias. So if we start from non-stationary state, there is so the Markov Chain Monte Carlo estimator is actually biased, and then we can reduce variance once we have reached the stationary state. Okay, and just as an idea that I won't really explore very much later on, is that we can either try to obtain some results that are sort of hold uniformly over a class of observables, or to specify to consider a specific observable. So if you're thinking of applications to, say, computational statistical mechanics, then it might be the case that you're actually interested in very specific observables. And whatever optimization results you might get over a class of observables might be very far from being optimal for the particular observable that you might be interested in. Okay, so as an example, and actually this fits nicely with the talk that we heard earlier today. So consider the case where I have a distribution that looks like this. So so the potential, if you like, has several characteristic length scales. So I want to sample from a distribution of this form. And we can either think of sort of this kind of glassy potentials that were discussed in the previous talk, or if you like, if you have a fast law system of stochastic differential equations, and then we know that in order to calculate the coefficients in the homogenized equation, we have to calculate averages with respect to the fast dynamics. But sort of it's mostly the sort of the application that I'm mostly interested in is situations where you have a potential that has several characteristic length scales. Okay. So yes. No, so there is a constant missing. You're perfectly right. So I should have written here proportional to this because, well, I mean, okay. It's still correct the way it's written because I can incorporate the constant in the exponential, but you're perfectly right. So there is a normalization constant here that is missing, and the whole point is that I don't want to calculate it, right? Okay, so here's a very simple example that, again, so it's actually, it fits nicely with the previous talk. So I can think of, say, take this sort of standard, well, lambda potential, if you like, and then I perturb, so the coefficient in front of the quadratic term has an oscillatory, contains an oscillatory part space. So this would correspond to, so here I have my potential, and then here's the corresponding probability distribution. So you have a sort of multimodal distribution, if you like. And then if you think of this not in one dimension, but I don't know, in 1,000 dimensions or whatever, then you can imagine that sampling from a distribution like this might be computationally quite expensive. And of course, I mean, one issue that again I want to address is that you might not want to sample exactly. So you might want to first homogenize, as we heard in the previous talk, and then sample from the homogenized distribution. In fact, we have some results in this direction that I will not really discuss about today. Okay, so the basic idea that I will, well, if you like, first let's just repeat the problem that I want to solve. So I want to calculate this integral in sufficiently high dimensions. And the distribution pi is known up to this constant that I don't want to calculate. And then I will use stochastic dynamics. And in fact, for what I will talk about today, I will consider only the continuous time problem. So rather than considering the actual sort of process that I will have to simulate on a computer, I will mostly consider the diffusion process. I'm assuming that the diffusion process that I will use, so it is ergodic with respect to the distribution from which I want to sample, and it has nice properties. So I have some sort of strong low-Flartz numbers that I can invoke in order to be able to calculate phase space averages in terms of long time averages. And in addition to this, I have a central limit theorem. So I have some information on the fluctuations around the mean. And so the sort of performance of my estimator, if you like, so it depends on two things. First, on how quickly I convert to the equilibrium state when I start from an arbitrary state. And second, on how large the asymptotic variance is, so how large this quantity is. Okay, and I want to discuss about some ideas. Yes, please.
Why is it, well, why do you want to calculate the expectation value of S?
Why, you mean?
You want to sample Y in the end.
Well, I mean, both problems, right? I mean, it's I either want to generate random numbers that are distributed according to pi, or I want to calculate integrals of this form. I mean, the two problems are very much related. Of course, you know, this is a very simple version of this basic algorithm, if you like. So if I really want to do this, then I have to, I mean, the natural thing would be to combine it with other kind of variance reduction techniques and so on. And I will comment on these things as we go along. Okay? Okay, so just to fix the notation then, so I will consider a stochastic differential equation, an Ito stochastic differential equation in finite dimensions. And then the generator is given by this formula here. And for what I will talk about today, I will mostly consider the case where sigma is strictly positive definite. But in fact, most probably this is not the right thing to do. So in terms of accelerating convergence to equilibrium and so on, most probably it's better to consider the sort of hyperelliptic case, if you like. Okay, so again, just to fix the notation, so this is the Fokker-Planck equation, so that governs, and again, I'm assuming that I have sufficient smoothness so that I can interchase between densities and measures and so on, so I won't worry about things like this. So I can either study the evolution of states of the system or of observables. And again, so going back to my earlier comment, so it might be that I have some, if I consider a very particular observable whose expectation I want to calculate, it might be that I can sort of optimize things with respect to this observable, and I can get a much better result than any result that it holds uniformly over the space of observables. And since I am assuming that everything is nice and smooth, so the diffusion process that I can use in order to sample from my distribution pi has to be such that the stationary Fokker-Planck equation is satisfied. Okay, so if you like, I have a sort of inverse problem. So I'm given the solution to this equation, and then I want to find the drift and diffusion coefficients so that this equation is satisfied. So I've rewritten the stationary Fokker-Planck equation here, and I might have boundary conditions, or I might also want to consider similar problems in infinite dimensions. So this is possible. And in fact, well, okay, so I will come back to this later on. And so of course, there are infinitely many solutions to this problem. So if I'm given the solution to this equation pi, then there are infinitely many drifts at B and diffusion matrices sigma, so that this equation is satisfied. Now, the first thing that I do, and it's actually quite standard, I mean, that we can do, and it's quite standard in in the Markov Chain Monte Carlo literature is to consider processes that are in detailed balance. Okay, so I consider reversible diffusions, if you like. So I'm assuming that there are no fluxes at equilibrium. In this case, my process is reversible with respect to pi of x. And in fact, so there are all sorts of different ways of defining a reversible diffusion process with respect to a probability measure. So for us, one useful definition is that the generator is self-adjoint in the L2 space weighted by the invariant measure. Okay, so this means in particular that you can do a lot of spectral theory, and that if you want to optimize quantities, I mean, if you want to accelerate convergence to equilibrium or minimize the asymptotic variance and so on, you can always use results from the spectral theory of self-adjoint operators. Right, so there is also a connection with having a zero entropy production rate, but this is not, I'm not going to use this. Right, okay, now, so let's first consider this kind of optimization problem, if you like, within the class of reversible diffusions. So here is the most general, well, at least uniformly elliptic diffusion process that is ergodic with respect to, and reversible with respect to the measure from which I want to sample. So notice there is this divergence term here. So if I assume that the diffusion matrix is state dependent, then there is this additional term that I need to consider here, and there is a logarithm missing from here. Sorry. So I can sort of optimize things over the space of symmetric positive definite matrices. So the standard choice would be to just take sigma to be the identity and then use the overdone Langevin dynamics. But it's not necessarily the optimal choice. In fact, in some sense, it's the worst thing that you can do. Well, I mean, first you define in what sense you want something to be the worst thing that it can be. And then, yeah, so I have to be a bit more precise when I say that this might not be the right thing to do. Okay, so then there are, I mean, many variants of this. So yesterday we heard about the underdamped Langevin dynamics, in fact, with the addition of a convolution term here. But in the sort of standard underdamped Langevin dynamics, then I have written it in this form, and now I can use this dynamics in order to sample from my distribution pi. So the marginal of the invariant distribution with respect to Q is precisely the distribution from which I want to sample. So first, it might be that actually this dynamics, even though, I mean, it's higher dimensional and it's not uniformly elliptic, that it has better properties. First, because it might be easier to solve it numerically. And second, because I already have a parameter with respect to which I can try to optimize things. So notice there is this friction coefficient gamma that does not enter into the formula for the invariant distribution. And for example, if I want to optimize convergence to equilibrium, I can choose gamma in such a way that the rate of convergence to equilibrium is optimal. Okay, so there is already a sort of a parameter here that I can play with. And I can keep going, so I can add additional degrees of freedom and have a sort of higher order Markovian models, or this so-called generalized Langevin equation. So, and then this means that I have additional parameters in my model that I can try to optimize over. Okay, so then if I add a non-reversible perturbation, then I can write the generator of my dynamics in this form. So this is the reversible part that I wrote earlier, and this is the non-reversible perturbation. So this drift gamma, that is basically the probability, the flux at equilibrium. So it's divergence free with respect to the measure pi. And one interesting observation is that if I write the generator in this form, then it decomposes nicely into the symmetric part that describes the reversible dynamics and the antisymmetric part that describes the non-reversible dynamics. This decomposition being in the weighted L2 space, so the L2 space weighted by the invariant measure. So then here's the corresponding stochastic differential equation. And again, I can ask sort of optimization questions with respect now to both the symmetric positive definite diffusion matrix sigma and the non-reversible drift gamma. So just to summarize, so just sort of some ideas on things that one could try. Either to just we could either try to choose optimally the diffusion matrix, or we could choose in a sort of optimal way that I need to make precise for the diffusion matrix and the non-reversible drift, or we can consider higher order Markovian models, or we can try to combine this kind of ideas with this so-called simulated annealing idea. So in fact, there are so many different options that somehow one has to be a bit careful and restrict the class of models that one considers. But it's certainly the case that we can do better than just using the standard overdamped Langevin dynamics. Okay, so now in addition to this, I mean, of course, at some point I have to discretize the system of equations, and even there I can play with things. So I can choose the right numerical scheme, and it's not necessarily the case that Euler-Maruyama is the right thing to do. And then, depending on how I choose to discretize these equations, then the corresponding Markov chain that I obtain might have actually better properties. Or I could try to combine all these things with an accept-reject step, but I will show later on that it's not necessarily a good idea. But in principle, I mean, it's something that I should certainly try. Now, the next question is, what do I mean when I say that I want to optimize my diffusion process with respect, so in terms of sampling from this distribution. So there are two things that I want to do, as I said. So first, I want to speed up convergence to equilibrium. And second, I want to minimize the asymptotic variance. So first, if we think about ways of measuring how quickly the system converges to equilibrium, then again, I have quite a bit of freedom. So the most natural choice might actually be to measure things in terms of relative entropy or total variation. But so I've written it here. I've written here the basic relative entropy inequality. So I will consider diffusion process for which I have exponentially fast convergence to equilibrium, and then what I mostly want to optimize is the rate of convergence to equilibrium, so this exponent lambda. Okay. So one first choice would be to say that, okay, I want to find the optimal diffusion process in terms of the rate of convergence to equilibrium in relative entropy. Of course, all these things that I will describe are very much related, and a natural question is whether all these different ways of measuring convergence to equilibrium lead to the same optimal diffusion process, which I will not discuss very much. So the one metric that I will mostly use, at least for the first part of the talk, is this so weighted L2 norm. So again, since I want to use spectral theory, I mean, it's natural that somehow things become easier if you use weighted L2 spaces. So the basic estimate that I have, so assuming that the probability, measure e to minus v satisfies the Poincare inequality, is this exponential estimate, and then I want to think whether by adding a non-reversible perturbation or by modifying the diffusion matrix, I can improve things on this basic inequality. So in the simplest possible version of my basic algorithm, which amounts to using the overdamped Langevin dynamics, this exponent lambda here depends only on the potential v. Okay, there are no parameters that I can play with. Okay. Then I could also use the Wasserstein metric, and in fact, well, one could argue that it might be better to measure convergence to equilibrium in terms of Wasserstein. So there's quite a bit of work that has been done in this direction in recent years, and also in sort of the connection between measuring convergence to equilibrium in Wasserstein, weighted L2, relative entropy, and so on. I don't want to discuss further about this topic, but one interesting, I think, question is whether whatever optimal solution I find to this kind of optimization problem, whether it's the same irrespective of the choice of metric that I'm using. Okay. Okay. So now, if I stay within the class of reversible diffusions, then I have a nice formulation for the sort of the quantity that I want to maximize. So I have a reversible diffusion, which means that I have a self-adjoint operator in the right L2 space, which means that I have a nice variational formula for the first non-zero eigenvalue, and Poincare's constant is precisely this. So the rate of convergence to equilibrium is determined precisely by this by the first non-zero eigenvalue, And then, so I can set up this optimization question that I have as a min-max problem. Okay, so I want to maximize over the space of symmetric matrices the first non-zero eigenvalue. So there is a clearer formulation of this problem. Now, how much you can do actually also in terms of sort of solving this problem numerically and so on is a different issue. But at least in terms of sort of formulating a very precise question, I think it's. Yes, so in fact, I will present some numerical experiments and some formulas in the one-dimensional case, because clearly if I send sigma to infinity, or, it's sort of Frobenius norm if you like to infinity, then this is the optimal choice. But of course, then, I mean, if I measure the actual computational cost, which is the right thing to do, I mean, clearly, my SD becomes stiffer and stiffer. So this, you're perfectly right. I mean, I should have written this here. So this is subject to the constraint that I'm fixing the sum norm of sigma. Okay. In fact, I can solve this problem more or less analytically in one dimension, and there it will become clear that I mean, I can say something. Okay, but yeah, you're perfectly right. So I should have included this constraint here, as I will do later. Okay, so right. So now it has been. Well, so there is some, at least numerical and theoretical work on this idea of using a space-dependent diffusion coefficient, and then this, again, so in connection to the previous talk, you can define some sort of Riemannian structure. I mean, so the metric tensor being this diffusion matrix and so on, and people have looked at this question. Oops, sorry. Here. It is reasonable to think that if we're back in this sort of metastable, picture, this, if I have a potential that has several metastable states and so on, that since I expect that my dynamics will spend a lot of, somehow this doesn't seem to, okay. Since I'm expecting that the dynamics will spend quite a bit of time at the local minimum of the potential, if I can sort of localize the temperature, if you like, so if I can sort of have a diffusion coefficient that is higher when I'm inside the well and lower when I'm outside the well and so on. This might help sample faster. If I can, provided that I can do this in a way that is consistent with sort of keeping the invariant distribution the same. So it is it is a natural sort of thing to try. Right, okay, so now, what the other question, the other approach, so if I separate the two issues of sort of optimizing over reversible diffusions and optimizing over non-reversible diffusions, that has actually been around for a long time, in fact, so is to actually introduce a non-reversible perturbation. So I take my basic Overdan Langevin dynamics, and then I add a drift here that is divergence-free with respect to the measure from which I want to sample. In fact, this B should have been a gamma. Sorry. Anyway, so okay. So I then consider this whole sort of one-parameter family, if you like, of diffusion processes that are parameterized by gamma. And in fact, there are lots of vector fields, gamma, that I can introduce that satisfy this divergence-free condition. And a standard example, I mean, in fact, you can write down the entire class. I mean, you can solve this equation if you like. So, I mean, if you're on the unitars, you can see how you can solve it using Fourier analysis. And then if you're in RD, you can also solve it. And then, so if I just take, if I multiply the gradient of the potential by an antisymmetric matrix, this is already sufficient so that I can, that this condition is satisfied. Okay? So now this problem becomes slightly easier, if you like, so in the sense that I can now optimize over the space of antisymmetric matrices as opposed to the space of vector fields. Now, the dynamics is no longer reversible, so detailed balance is not satisfied. But this is not necessarily a problem. So, I mean, the dynamics is still ergodic with respect to the distribution from which I want to sample. And I can use this kind of modified dynamics. Now, in this standard sort of Metropolis Hastings version of the Markov Chain Monte Carlo algorithm, of course, the accept reject step is introduced precisely so that the Markov chain is reversible with respect to the distribution from which I want to sample. But yeah, it's not necessary. So, I mean, I can consider this kind of non-reversible dynamics. So again, I can set this up as some sort of an optimization problem, and then, or min-max principle, if you like. And then again, I have to be a bit careful about whether I should fix, say, the weighted L2 norm of the vector field gamma or not. But it might be that one can make some progress in understanding all these questions by considering some sort of an abstract sort of perturbation problem, if you like, in spectral theory, that I have my self-adjoint operator S are perturbed by a non-self-adjoint, by an antisymmetric operator that preserves the null space of S, and then I ask whether there is an optimal choice for A in terms of maximizing the first non-zero eigenvalue. Okay. However, as Tony and Francis and I learned the hard way, somehow spectral information is not sufficient for non-reversible diffusion, so you need to be able to say a bit more. Right. Okay. So there are lots of. So this question is also this kind of sort of optimal choice of the non-reversible perturbation appears in the context of fluid transport and mixing and so on. And I mean, there are many papers in this area. So there's, for example, this work by Constantine and collaborators where they introduce this concept of relaxation enhancing flow, and they want to find what kind of, sorry, in my terminology, what kind of non-reversible perturbations are such that basically you can, you can accelerate the mixing rate and so on. But all this, these works are mostly related to sort of asymptotic results in the limit as the strength of the non-reversible perturbation goes to infinity, as opposed to finding the optimal solution. Okay? But there is a very large literature in this problem. Okay, so now what I was saying earlier, that the reversible case is the worst, and what I mean by this is that so this basic L2 estimate that I showed earlier, this, of course, it's valid also if you add a non-reversible perturbation, because of course the L2 estimate does not see the antisymmetric part, which means that you cannot do worse, right? So I mean, here's the proof of the result that non-reversible dynamics is the worst thing you can do. I mean, again, it's not really a precise statement, and later on actually also that you have to, you need additional information, but basically that's it. So if you add a non-reversible part, so this estimate is still valid. So you're certainly not making things worse. Of course, if you add a non-reversible perturbation, then you have to be careful about solving the resulting stochastic differential equations and about their stiffness and so on. And in fact, I will discuss about this later on. So again, there is a very long, there is literature on this topic of sort of Poincare logarithmic Sobolev inequalities for non-reversible diffusions. So there are, so I have written some names here. And the intuition is that if I add a Hamiltonian part, or whatever you want to call it, a non-reversible part to the dynamics, then this might actually help me escape from metastable states. This is the idea that I want to explore. Right. So that's a very, very simple example. And in fact, this might be a very boring example, because I just take this two-dimensional potential that is, in fact, Gaussian in Y. And I just compute the second moment. And there is, so we add this non-reversible perturbation there, so delta times J. And there is no discussion about optimizing things. So I'm just going to try it with different strengths of the non-reversible perturbation. And this is the sort of thing that you get. So the blue curve corresponds to the reversible dynamics, and then the black curve to a particular choice of the non-reversible dynamics, so delta equals 10. And on one hand, of course, now we're not in the self-adjoint or normal, if you like. So the operator is far from being normal. So this means that I have oscillations at the beginning. And then in the end, I do reach the sort of asymptotic value of the second moment faster than what I would do with the reversible dynamics. But of course, I mean, here, there's a very small improvement. So I hope that I can actually really do better, much better, by choosing the non-reversible dynamics the right way. Right, so the crucial point now is that, as I said, so if, I mean, with this version of the basic L2 estimate, okay, so this is really officially not working. So, yeah, okay. So with the official version, with the basic version of the L2 estimate, so there's not much that I can tell from there, right? So it's the same for reversible and non-reversible diffusions. So in the non-self-adjoint case, it's not only, I mean, I need to introduce a constant in front of the right-hand side, okay? This constant is equal to 1 in the self-adjoint case, but it's greater than 1 in the non-self-adjoint case. So on one hand, I hope that by choosing the right non-reversible dynamics, I will, some lambda bar will be greater and hopefully much, much larger than lambda, but there will be a price to pay, namely that there will be a constant in front that might actually be quite nasty looking. Okay, so this is the sort of modified estimate that we need to consider. And one can provide a sort of complete solution to this problem for Gaussian, for sort of linear diffusions corresponding to Gaussian distributions. Of course, you will tell me, I mean, we know how to sample from a Gaussian, and why are you wasting our time? But somehow this is, if you like, a starting point for hopefully looking at more complicated distributions. So, okay, so let me repeat. So in the linear case, I can actually provide a more or less explicit solution to this question of choosing the optimal non-reversible perturbation. And in fact, it turns out that it's basically a problem in linear algebra. So here's the stochastic differential equation that I want to consider, this equation 31. So S is the inverse of the covariance matrix of my Gaussian distribution, and Z is the antisymmetric matrix that I want to choose in an optimal way. Now, so let's see what can go wrong in this case. Well, the only thing that could lead to a slow rate of convergence to equilibrium is if the covariance matrix or its inverse, the precision operator, have very small eigenvalues. Okay, the smallest eigenvalue will determine the rate of convergence to equilibrium. So hopefully by adding this antisymmetric matrix A, I can sort of rotate things so that all eigenvalues have the same real part. Okay, so there is no preferred direction, if you like. So there is no direction through which the dynamics might slow down. So well, so okay. So for Gaussian diffusions, there is some sort of equivalence between all kind of relative entropy metrics that you can use. But so here I'm discussing things, but this is kind of an aside, if you like. So I will present results for the convergence to equilibrium in weighted L2 that depends only on the eigenvalues of the matrix S. And this is actually precise results. I will present this. So the only information that you need in order to determine the spectrum of the generator of the dynamics, not only the first non-zero eigenvalue, is the eigenvalues of S. Okay. So, so here is then the result. So in fact, there is an optimal solution to, first, there is an we know what the optimal rate of convergence to equilibrium is, and this is the average over all eigenvalues. So as I said, the problem is if there are small eigenvalues, so if I can rotate things so that all eigenvalues have the same real part, then this means that this is the optimal, is the best I can do. So in fact, I can actually solve this min-max problem. So there exists an optimal antisymmetric matrix so that I can get this optimal bound. And then in terms of matrix exponentials, I get my optimal exponential rate, so my optimal rate of convergence to equilibrium. And then there is a constant in front that depends on the number of dimensions in which I am and also on the condition number of kappa. Okay? As I said, I really need to keep careful track of this constant here. And this will depend. And in principle, at some point, I would also like to be able to lift this up to infinite dimensions. I mean, to think about sampling from random fields. So I need to know how the constant depends on the number of dimensions. And I also, for this particular case, I need to know how it depends on how ill-conditioned the covariance matrix or the precision matrix of the Gaussian from which some sampling is. No, I mean, I will present some numerical experiments, and you'll see how this works. But is it realistically, of course, I mean, you don't want to use this kind of ideas for a Gaussian diffusion, right? So the only case I can think of this as being a sort of interesting idea in terms of, like, for practitioners, if you like, is if you want to use this to sample from Gaussian random fields. So if you can get good control on the dependence of this constant on the number of dimensions, hopefully you might be able to say something about sort of stochastic, linear or stochastic partial differential equations. Okay, but at this stage, it's kind of an exercise to see that somehow non-reversible perturbations might help. Right, okay, so now this is the sort of crucial part. So if I can solve the linear algebraic problem, then it's sufficient to solve the full problem because, as I said, so the spectrum of the generator and of the Fokker-Planck operator of linear diffusion process depends only on the eigenvalues of the matrix that appears in the drift. Okay. So in particular, I can, so the optimal rate of convergence to equilibrium, not in terms of matrix exponentials, which, I mean, so this would correspond to the first moment, if you like, but in terms of weighted L2, of the weighted L2 norm, is again the average of the eigenvalues. And, excuse me, by using this result, I can actually prove an exponential rate of convergence for observable. So I take the semigroup generated by the generator of the dynamics with the optimal choice of the antisymmetric perturbation. And I have here the optimal rate of convergence and a constant in front that depends on sort of the smallest eigenvalue, if you like, in a polynomial way. So, and then I have some information on the scaling with respect to the number of dimensions. And based on this, then, I can also prove a similar result for the laws of the processes, or for the solution to the Fokker-Planck equation, which again is the same. So I have the right exponential term there and a controllable constant in front. Okay, so this is it. So the way to prove this result is first by solving the linear algebraic problem, then use the fact that the spectrum of the generator depends only on the eigenvalues of the matrix that appears in the drift, and then try to control the constant in front. So I don't think I want to get too much into this. Let me just say that one can turn this into an algorithm for actually obtaining the optimal non-reversible perturbation. So one can show that this requirement that we have there, so that the spectrum of our matrix, actually its real part, lies along the sort of, is equal to the average of the eigenvalue. So it's equal to writing down this kind of linear algebraic equation, which in turn, so I can use now this equation in order to actually develop an algorithm for calculating the optimal non-reversible perturbation. So, okay, I'll skip this, but there is an algorithm, well, okay, so there is an algorithm that I can use, that I can develop in order to calculate the optimal antisymmetric matrix A, which I will show in a second. Let me discuss about the second point of how the spectrum of the generator is related to the spectrum of the matrix P. So this is true, actually, even in the case where I have a non-trivial, well, constant but not trivial diffusion matrix sigma. And in fact, even in the case where the generator is actually the generator. I mean, so it has a hyperelliptic structure, but is not uniformly elliptic. So as long as I have this kind of linear structure, so it corresponds to a Gaussian invariant measure, then the spectrum of this operator can be calculated explicitly in the L2 space weighted by the invariant measure, and it looks like this. So I take integer linear combinations of the eigenvalues of the matrix that appears in the drift. Okay. Now, of course, I mean, in the case where the diffusion matrix is strictly positive definite, this is not a great surprise because the generator of linear diffusion process is unitarily equivalent to this Reversible operator for the harmonic oscillator. Okay, and I mean, of course, we know that there is a similar formula in weighted in the flat L2 space, in fact, for the spectrum of the Reversible operator for the harmonic oscillator. Okay, what might be slightly more surprising is that you have the same result also in the sort of hyperelliptic case, and that in fact this formula is completely dependent of the diffusion matrix. Of course, the space in which you study the spectrum depends on the diffusion matrix because it's in this weighted L2 space or LP space, but not the actual formula. Okay. So, by the way, I mean, an interesting, or I don't know, perhaps not so interesting exercise is to use this formula in order to calculate the spectrum of the generator of the underdamped Langevin dynamics for a harmonic potential. And then you can optimize the first non-zero eigenvalue with respect to the friction coefficient. Right, okay, so this result goes back to Metafuna, Ballara, and Priola. So we have an alternative proof with Michaela and with Karel, Pravda Starov. Yeah, I don't want to get into this. And in fact, there is some hope that you might be able to do similar things with linear stochastic partial differential equations, because there is a similar formula also in infinite dimensions. Okay, in fact, I have a student who's working on this at the moment. And there, as I said, they might even become mildly interesting for practitioners. I mean, if you know how to, if you can develop an algorithm for sampling from Gaussian fields. Okay, and then there is a third part on sort of controlling the constant in front. And okay, yeah, I don't want to discuss about this. So, okay, so here's the algorithm then for obtaining the optimal non-reversible perturbation. I don't want to get into the details, but the point is that somehow you can solve with pencil and paper the two-dimensional problem, and then you can iterate. Now, this group by Huang, so they have an alternative, so after this work, so they developed an alternative algorithm for obtaining the optimal non-reversible perturbation that does not require a Gram-Schmidt step that can be unstable. But in any event, so here's the algorithm, and here are two examples. So first, I take a 100 by 100 diagonal matrix with random entries, which are uniformly distributed in 0, 1. So this will be the inverse of my covariance matrix. And for the particular realization that I will show, so the spectral gap is there, so it's 10 to minus 3. And then if I use this algorithm for calculating the optimal non-reversible perturbation, I gain basically 2 orders of magnitude. Okay, so here's that's the first moment, and the red curve corresponds to the optimal non-reversible dynamics, and the black curve to the reversible dynamics. Okay, I mean, yeah, I don't know. Of course, this is a very artificial example, but in this case, you can improve things a lot because you go basically from, yeah, so the smallest eigenvalue to the average overall eigenvalues. So if I take now a stochastic, so the stochastic heat equation, and then I take it in the interval 0, 1, and with there's the boundary conditions, and then I take a standard centered finite difference approximation. So then this actually leads to an unstable Olympic process in finite dimensions. And again, I want to compute the first moment, and then you can see that in principle I can sort of gain several orders of magnitude. Okay, of course there is this initial transient behavior that is not nice, but eventually it converges much faster to its equilibrium value. Okay, so there are, as I said, so since then there's been quite a bit of work on this problem. So, and there's some nice work by Luke Rabel and Kostas Filiopoulos where they make a connection between this question of sort of optimizing the choice of the non-reversible perturbation with the theory of large deviations. Right, so this is very nice work. Right, so now I want to move to the second part, which is how to minimize the asymptotic variance. And right. So, and the two issues might or might not be separate. So, in the sense that the diffusion process that leads to the fastest rate of convergence to equilibrium might not necessarily lead to the minimum asymptotic variance. And in fact, for Markov chains, there is sort of an ordering that has been, well, partial ordering that has been introduced. So, if you take the space of all Markov chains that are, say, for example, reversible with respect to the probability distribution from which you want to sample, then you can use these two ideas in order to actually introduce what turns out to be a partial ordering in this space. Okay, so basically, what eventually we would like to do is to introduce a similar idea for diffusion processes, and there are lots of questions. For example, whether the two orderings based on 1 and 2 are equivalent. It seems that they are for reversible diffusions, but not necessarily for non-reversible diffusions. So now, if I want to analyze this formula that I have for the asymptotic variance, so it depends on the observable f, but it also depends, of course, on the generator L. And this is actually very similar to the formula that we get from homogenization theory for the effective diffusion coefficient in sort of convection diffusion problems. Okay, basically, it's the same. It's just that in the case of, well, turbulent diffusion or advection diffusion equations, whatever you want to call it, the choice of the observable f is fixed. But it's not, I mean, this is the only difference. And this is a problem, of course, that has been studied quite a bit. So you can use known results in order to analyze this formula, and in particular, the dependence of the asymptotic variance on the non-reversible perturbation, for example. And so some time ago, I did some analysis, again, in a very different context, but it turns out that somehow this is the, yeah, so you can use tools that have already been developed in order to analyze this formula. So for example, it's very easy to actually show that the asymptotic variance is reduced if you add a non-reversible perturbation. And this is already showing this work by Luke Ray, Belen, Kostas Spiliopoulos. They have actually this result using different techniques. But yeah, I think for Markov chains, it is well known. But this is just an application, if you like, of this sort of kind of spectral analysis that you can use in order to study these problems. And for example, you can obtain the result that the asymptotic variance is always reduced if you add a non-reversible perturbation. Let me again emphasize the fact that this does not provide us with any information about the actual computational cost, because at some point I will have to solve all these equations numerically, and I have to compute averages and so on. But theoretically, at least, if I add a non-reversible perturbation, I'm not going to do worse. And another observation, so for the asymptotic variance, I mean, this is certainly an L2, a weighted L2 result. So here there's no ambiguity as to how I should be measuring things. I mean, the asymptotic variance is given in terms of the weighted L2 norm. Okay, so okay, so then I can write down a formula for the asymptotic variance that is based on the solution to a Poisson equation. This is what I meant when I said that it's basically exactly the same formulas that you have in homogenization theory. So if I can solve in some way this Poisson equation, then I can substitute the solution back into the formula for the asymptotic variance and then obtain information. Of course, if I knew how to solve this PDE, then there wouldn't be any reason to sample from anything, right? So, but I don't need to solve it exactly. I can either solve it approximately, or I can just get some information, just obtain bounds on solutions to this equation and so on. And in fact, yeah, there is a nice trick that one can use. So you can introduce an appropriate compact operator by just multiplying through by the reversible part of the dynamics. So you have a reversible, so the self-adjoint part of the dynamics corresponding to the reversible part, which is a second order operator. A corresponding to the non-reversible perturbation is a first order operator. So you hope that this S inverse A will be bounded, and if you're lucky, it will be compact. So you can do some quite explicit analysis and obtain formulas, in fact, for the asymptotic variance in terms of the eigenvalues of this compact operator that you're introducing, and also the strength of the non-reversible perturbation that here is denoted by alpha as opposed to delta. Okay, so again, this, if you look at papers from the late 80s, early 90s on turbulent diffusion and so on, similar formulas appeared there, not in this kind of general context, but again, so as I said, so this is a problem that has been studied in sort of in this context of turbulent diffusion. So then you can obtain asymptotic results, get estimates, bounds, and so on. And so here are some examples. So I take this free well potential here, which I think has been used by Christoph Suter and Eric van den Eyden and so on for testing several ideas. And then I take the second moment, and I want to see whether my non-reversible, the addition of a non-reversible perturbation actually reduces the variance. And as I said, so one thing that sort of from a natural idea would be to combine using a non-reversible perturbation with an accept-reject step. Now, of course, if I include an accept-reject step, then the corresponding Markov chain is reversible. And this result here is telling me that I'm certainly not improving things. But still, I mean, it's something that one has to check. So let's also check this. So I'm going to consider sort of arbitrary non-reversible perturbations of the overdone Langevin dynamics for this 3-well potential. And at the same time, I will also test the idea of using a non-reversible proposal, if you like, but then sort of metropolizing things. And I don't know. You might think that it's obviously the wrong thing to do, but anyway. So I mean, we can test it. And okay, so here's how this 3-well potential looks like, and here's what we get. So the blue curve is the asymptotic variance as a function of the strength of the perturbation for the unadjusted dynamics, so without the metropolis Hastings step. So variance is reduced. Now, of course, whether this amount of variance reduction is sufficient to may convince you that it's a good idea to use non-reversible dynamics is a different issue. But as I said, I mean, at this stage, all these algorithms that I'm presenting are in their simplest possible form, right? So one can improve things, so one can use additional variance reduction steps and so on. Anyway, and then, so if I adjust things by adding the accept reject step, then I'm not doing anything. So it's the green curve. And of course, if you have a theorem that is telling you that this is the case, why bother doing any numerics? But anyway, it is what it is. So now let's look at a slightly more interesting example. So I take this so dimer in a solver. So the potential is the standard Lennard-Jones potential, and so for the dimer pair, I have this kind of interaction potential. There are all sorts of parameters in the problem, but so here is a sort of slightly larger, if you like, test case or a toy model. And the question is again whether by just since in this case it's not really it's not realistic to expect to be able to obtain any kind of optimal non-reversible perturbation, whether we can at least, just if you like trial and error, we can find a non-reversible perturbation that will significantly reduce the variance. Right, okay, so some more details about the calculation, and here's the reaction coordinate whose statistics we want to calculate. Here is the non-reversible perturbation. So the antisymmetric matrix A has this structure, and the zeros are 4x4 zero matrices, and R is consists of this kind of 4x4 rotation matrix. Right. So here's the here's the histogram of the reaction coordinate, and here's what we get in terms of the autocorrelation of the dimer model as a function of the time lag, and this is for different values of the strength of the perturbation. So again, it seems that as we increase the strength of the perturbation, so we're doing better. But as I said, this is not the full story because I need to really carefully monitor the computational cost. Okay? But at least there seems to be some hope that somehow. No, it's actually for that's the reaction coordinate, in fact. Well, I mean, so it's. Yeah, it is the end-to-end distance thing. Yeah, okay. And this is the asymptotic variance, which again for as a function of alpha, and again, so you see that it decreases, but it decreases not very much. It's like 25%. So okay. So now, as I said, so I mean the honest test is to actually measure the computational cost. Because so if I add a strong non-reversible perturbation, then my SDs become stiffer, and then I have to reduce the time step. So I have to monitor the computational cost. Without getting into any details, and this is actually quite preliminary, let me just say that, in fact, in this kind of vanilla version of all these algorithms, it's still the case that reversible dynamics is doing better in terms of the computational cost. So, okay, so I don't have enough time to get into the details, but if I measure the error that I'm actually committing for a fixed sort of computational budget, if you like, so if I fix my resources and then I measure the error that I'm committing for different values of alpha, and given the fact that the resulting stochastic differential equations will have to be solved accurately, and as I increase the strength of the non-reversible perturbation, I might, in fact, have to use a smaller time step. Then it might be, in fact, as I said, that the lowest computational cost is achieved by this black curve that corresponds to the reversible dynamics. So, as I said, this is very, very preliminary, but I just want to show that, in my opinion, this is the right test to run. Okay, so I mean, we need to measure whether we're actually reducing the computational cost. Okay, so very quickly, just one last topic. So all these things. So as I said, so ideally, one would like to introduce some sort of ordering over the space of diffusion processes that are ergodic with respect to a given probability distribution. And in one dimension, you can do all these things by hand. So there is some nice recent work by Roberts and Rosenthal where they ask this question. So they consider this as some sort of a diffusion limit of a standard sort of Markov Chain Monte Carlo algorithm. And then they want to ask how the asymptotic variance depends on sigma. And the way they, on the strength, on the diffusion coefficient, the way they study this is by discretizing things and going back to the sort of Markov chain world. But this is the sort of thing that is actually, I think, better studied using Dirichlet forms and things like that. So in one, and in fact, you can do this also in arbitrary dimensions, but let me just show you an elementary calculation in one dimension. So I ask the following. So if I take this one-dimensional diffusion process that is ergodic with respect to pi for all choices of sigma, and then I ask, so if I assume that, say, sigma 1 and sigma 2, so that sigma 1 is always greater than sigma 2, so uniformly in X, what can I say about the asymptotic variances? Okay, and this is what they call efficiency ordering. And in fact, it happens what you would expect. So if sigma 1 is always greater than sigma 2, so uniformly in X, then you have exactly the reverse for the asymptotic variances. Okay. Now, as I said, so you can study similar problems in higher dimensions, and this is a nice application of all these kind of Dirichlet form ideas and so on. But in one dimension, you can just compute things explicitly. So you can use this Poisson equation that I introduced earlier, that you can define the asymptotic variance in terms of solutions to this equation. You can solve this equation, and then you can obtain a nice formula for the asymptotic variance that has the right scaling. Oops, sorry. No. That has the right scaling in terms of pi and so on, and capital F is kind of the antiderivative of F, but again, with respect to the invariant distribution pi. And right, so using this formula, you can obtain this kind of ordering with respect to the diffusion coefficient, and then you can solve the optimization problem. And they come back to the earlier comment that, of course, if I heat up my system, then this will improve things, but I cannot really do this on the like when I simulate things. So I fix the weighted L2 norm of the diffusion coefficient, and I can actually solve the corresponding Euler Lagrange equations and so on, and obtain a formula for the asymptotic variance that depends on the observable. Okay, as I would expect. Okay, and K is the L2, the weighted L2 norm of the diffusion coefficient, or its square, rather. Okay, so I mean, of course, all these things. I mean, one would be interested in doing them in higher dimensions, and as I said, there is some hope. I mean, so once you have a PD that you can write down through which you can express the asymptotic variance, then you can use also tools from the theory of PDs, calculus of variations, and so on. Okay, so just very briefly to summarize. So first, in principle, we can accelerate, well, speed up convergence to equilibrium and reduce the asymptotic variance by choosing the right dynamics. So if you like, there's some sort of a variance reduction idea in which rather than doing, I don't know, importance sampling or anything like that, so you're actually choosing the right dynamics. It might be beneficial to use non-reversible diffusions in Markov chains, but as I said, one has to be a bit careful on how one implements these algorithms and how you measure the computational cost and so on. And of course, you wouldn't just want to choose the right dynamics. You would also want to combine this with either variance reduction techniques or simulated tempering and so on. In fact, we're looking at things like this at the moment. And for example, there is this version of MCMC called zero variance reduction MCMC, and you can combine this with this kind of ideas. And it seems that it can lead to quite interesting results. And there's no reason why you should use overdamped Langevin dynamics. In fact, I think there are many arguments in favor of using either underdamped Langevin dynamics or even higher order Markovian models. And there you also introduce parameters, functions, and so on with respect to which you can optimize things. Okay, I'll stop here. Thank you. Well, so you have this general result, as I said, that whatever you add there, I mean, you will definitely not make things worse. If you can, if your question is whether you can say you can get some more detailed information, or in particular find where the optimal non-reversible perturbation is for in the non-quadratic case, that I don't know. I mean, it doesn't seem to be possible to say something in sort of in a very general, for a very general class of potentials. But yeah, this is certainly the question to ask, right? So. Yes, so in the nonlinear case, I mean, I can tell you one thing that we have done and it seems to work. So if you have a bistable potential and you are in the semi-classical regime, then you have quite detailed information on how the spectrum looks like and so on. So you can try to separate the two wells and solve the two optimal problems and then pass things together. So you can try all sorts of things. But whether one could prove something in a very general framework, I don't know. I don't know. So this estimate that I showed here, where is it? It shows like, well, so the dependence is polynomial. Now, in this estimate that I showed here, I think it's an n-cubed scaling. Whether this is optimal or not, I mean, you can ask. Mm-hmm. Yeah. I'm not sure whether you can do this because, you see, so again, there are many, many different matrices that have this, whose spectrum has the same real part, right? So again, I mean, even in this optimization question here, I mean, you still end up with too many solutions, and then you want to optimize over them. If you could say something better than this, it might be. I'm not sure. I'm not sure though. Or I mean, what you're asking, I understand, is slightly different. So whether you can say, okay, I'm happy not to have the optimal rate of convergence to equilibrium as long as I have better control of the constant in front. Yeah, we haven't tried it. I don't know. It might be possible.